Hello everyone, my name is Nithya Sharma and my registration number is 19MIA1028. I'm here to present my assignment on Nand2Tetris Project-1 Boolean Logic under the guidance of Professor Abdul Quadir for my digital assignment 2 in operating systems. So I'll be taking references from the official website of Nand2Tetris. So basically I'll be downloading the software. I've already downloaded it, so I won't be downloading it again. All the software tools of Nand2Tetris are equipped with Java runtime environment. So if you do not have one in your system, you can download it from here. So this is a project that actually consists of 12 parts, in which we'll be performing only the first project in this video, that is Boolean logic. So once you download the software, you can see a folder called Nand2Tetris, in which you can see two folders, project and tools. We'll be performing project 1, and these are the necessary scripts and text that will be needed. This is the coding file. The coding file will be empty. You will have to type in the code. Okay. The tools that will be necessary for this project are also available. For the first project, we'll be only using the hardware stimulator that is run on Java runtime environment. I've already downloaded that as well and installed it. This is what it looks like. Okay. Moving forward, in the first project, we will be given NAND gates, and the goal is to build the following 15 gates under the three headings: elementary logic gates, 16-bit variables, and multi-way variables. First, let's look into what is a NAND gate. A NAND gate is an opposite of an AND gate. That is, if the inputs are two zeros, the output is going to be 1, and if the inputs are two ones, the output is going to be 0. And if it's 0, 1, it's going to be 1, and if it's 1, 0, it's going to be 1. Now let's look into the 6 elementary logic gates. The first being a NOT gate, which is basically an inverter. That is, if the input is going to be 0, the output is going to be 1, and if the input is going to be 1, the output is going to be 0. This is a realization through NAND gate. It means that we make a NOT gate using a NAND gate. So now let's run the program and see if it is the same. So NOT gate, first let's load in the chip. Next the script for NOT gate. And this is how you run the program. This yellow line is basically shows us at that particular time which line of code is being run. If it is not stopping in between, it means that there is no problem with the code. So now it's finished running, and now let's look into the output. This is the output we have got, 0, 1, 1, 0. Now let's compare it. It's correct. So there's no problem with my code, and I've got the correct output. Next, it is the AND gate. AND gate, as I've said earlier, is the opposite of an AND gate. That is, if the inputs are going to be 0, 0, the output is going to be 0. If the input is going to be 1, 1, the output is going to be 1. And if it's going to be 0, 1, it's going to be 0. And if it is 1, 0, it's going to be 0. And this is a realization through NAND gate. Now let's load in the chip for AND gate. Load. Let's load the script for AND gate. Running the program. There's no problem with the program flow. Now let's look into the output. This is the output that's given. Now let's compare it. It's correct. So moving forward, next is the OR gate. The OR gate is, if you have two inputs, is going to be 0. 0, then it's going to be 0, and if it's going to be 0 1, it's going to be 1, and if it is 1 0, it's going to be 1, and if it is 1 1, it's going to be 1. This is a realization through NAND gates. Let's load in the chip for OR gate and the script, and now let's run the program. I've already written the necessary codes for this chip and for the script, because of which I'm not writing it as I'm performing. Make sure that you also write this necessary code and everything before you start running the program. So this is the output I've got. Now let's compare it. It's the same. So let's move forward to the next one. Next is an XOR gate. An XOR gate is basically NOT gate plus OR gate. That is, if you have inputs as 0 0, the output is going to be 0, and if the input is going to be 1 1, the output is going to be 0. That is, if the inputs are similar, both the inputs are similar, then we get 0, and if the inputs are the opposite, then the output is going to be 1. So now let's load in the chip for XOR. Loading the chip. Now it's okay. Running the program. Let's look into the output. This is the output we get. Now let's compare it. It's the same. So let's move on to multiplexers. We'll be looking into multiplexer and demultiplexers, both of which can be made using any gates, but these two are made using only NAND gates, because we are only given NAND gates. Okay, so let's load in the chip for multiplexers, the script for multiplexer, and now let's run the program. There's no error, so let's look into the output. This is the output we get. Now let's compare it. It's the same. So now let's look into demultiplexers. Demultiplexer, you can also call it as demux. Okay, so let's run the program. Output, and now compare. It's the same. So next we'll be looking into 16-bit variables, in which we have 4 gates, not 16 and 16, or 16 and mux 16, multiplexer 16, that is. Okay, so first we'll be looking into not 16, loading in the chip. Next, the script for not 16. Now let's run the program. There is no error, so now let's look into the output. This is the output we are getting in 16-bit. Now let's compare it. It's the same. So the next one that we'll be looking into is AND 16. Load chip. Next we'll be loading the script and running the program. There's no error, so let's look into the output. It's a 16-bit output. Let's compare it. It's the same. So moving forward to the next one. Next is OR16. Let's load in the script. Running the program. Let's look into the output, the 16-bit output, and now comparing it, it's the same. So our code and program is correct. So the next one is the last one, that is the MUX 16, multiplexer 16, loading in the chip and the script. Let's run the program. Now let's look into the output. Okay, and let's compare it. The 16-bit output is correct. So next we'll be looking into multi-way variables, under which we'll be looking into 5 variables. 5 gates, or 8-way, MUX 4-way 16, multiplexer 4-way 16, multiplexer 8 4-way 16, demultiplexer 4-way, demultiplexer 8-way. Now let's load in the chip for OR 8-way. Loading in the chip. Now let's load in the script for OR 8-way. Running the program. There's no issue with code, so let's look into the output. This is the output we get, and now let's compare it. It's the same. So moving forward to the next one is a multiplexer 4-way 16-bit. Multiplexer 4-way 16-bit chip. Okay. Let's load in the script. Multiplexer 4-way 16. Running the program. There's no issue with the code, so let's look into the output. It's a 16-bit output, way 16. Now let's compare it. It's the same. Moving forward to the next one. The next one is a multiplexer 8-way 16. Loading in the chip, loading in the script. Let's run the program. There's no issue with the code, so let's look into the output. Okay, now let's compare it. Okay, it's correct. So next, moving forward to the next one is the demultiplexer 4-way. Demultiplexer 4-way, loading in the chip, loading in the script for demultiplexer 4-way, running the program. Okay, let's look into the output. Okay, now comparing it, it's the same. Moving forward to the next one is the last one, demultiplexer 8-way. Loading in the script. Running the program. there's no error with the code. So let's look into the output. This is the output. Now let's compare it. It's the same. So that would be all. Okay, that will be the end of project 1. Thank you.